Welcome back. In the previous session, we had seen how we can use meta-heuristic techniques to solve black box optimization problems, and there we had also mentioned that the fitness function can actually be evaluated by executing some other software, right. So, very often what happens is the evaluation of fitness function can be time consuming. So, those are called as expensive optimization problem, right. So, and this meta-heuristic techniques, if you have seen, so for example, if we were to use TLBO with a population size of, let us say, 10 and 5 iterations, right. So, even in that case you will have to do 110 times the objective function has to be evaluated. Let us assume that the evaluation of each objective function actually takes, let us say, 5 minutes, then we are looking at 110 into 5 minutes. So, that would be the time required just for even calculating the objective function, right. When compared to calculation of the objective function, say 5 minutes for one solution, the time required for all the rest of the operation is almost negligible, right. This is very often considered a drawback of meta-heuristic techniques, right. So, that it requires too many functional evaluations of the objective function. In those cases, we can actually employ parallel computing, right. Most of your computers would have multiple cores, right. So, all the cores can be put to use for evaluating the fitness function. So, for example, consider the very first step wherein we need to generate, let us say, 100 population members, right. Once we generate the 100 population members, the fitness function of each member is to be evaluated, right. The fitness function evaluation of the first member and the second member, the third member, the fourth member, all of these are independent, right. So, the fitness function value of the second population member does not depend on the fitness function value of the first member, right. So, what we can do is, if we have multiple resources, we can actually split the population into multiple and use one resource for each, right. So, to better understand this, consider an experiment, right. Let us say an experiment takes 5 minutes to give us the fitness function value. So, in that case what we can do is, if we have multiple setups, we can perform the experiments parallelly. If the evaluation of your objective function is to be done on a computer, right, then since there are multiple cores, we can make use of the different cores, right, to evaluate the fitness function of each solution. So, that is what we will be looking into this, right. So, here we will be using the parallel computation toolbox of MATLAB, right. Parallel computation toolbox of MATLAB has many features. Here we will be just touching upon only one of the function, which is par_for. So, before going into optimization, let us just look how to use par_for in MATLAB. So, here what we are doing is, let us say I have an function, right, the name of the function is expfun, it accepts two variable, right, and it returns a scalar value f. So, this is more like our objective function. Let us say it accepts two input arguments, right, as a vector, right. So, 3, 4, right. So, f is equal to 25. So, here it actually takes some time to calculate this, right. So, since I calculated only once, you did not see the time difference, right. So, let us say I want to calculate it for 500 times. So, what we are doing over here is, we are defining d is equal to 2, lower bound we are saying is minus 5.12, upper bound we are saying it is 5.12, and then we are saying prob is equal to expfun, right, and we are fixing the population size as 500. And here we are generating the population. At the end of line 10, we will have a matrix having 500 rows and 2 columns, right. The task is to find out the fitness function of every member, right. So, to find out the fitness function of every member into the fitness function file. So, for example, in this case, prob is the name of the function handle, right. So, what we are doing is, we are passing the pth row of the population matrix P to the problem, which is expfun, right, and we are saving the fitness function in the second column of the vector f, right, and we are changing every row, right. So, this is what we want to do. So, now if I execute this, you will be able to see that it requires some reasonable amount of time. So, for example, this tick is a MATLAB inbuilt command, right. So, assume that as soon as MATLAB encounters this tick, it starts a stopwatch, and as soon as it encounters a talk, it is going to stop that stop clock, right. Additional help on tick and talk, you can go and look by just doing help tick and help talk, right. So, right now you can assume that the difference between this tick and this talk will tell us how much time is required to calculate the fitness function value of this 500 members, right. So, if I execute this, So as you can see, it actually is taking some time, right. So here if you see, it's written busy, so it is actually calculating the fitness function, right. So this can happen. So many of your optimization problems, particularly real world optimization problem, the evaluation of fitness function may actually be time consuming, right. So in those cases, how to use parallel computation to overcome the drawback of meta heuristic techniques, that is what we are looking in this session. As we can see, it is still taking some time to evaluate it, right. So right now we are not employing the parallel computation feature of MATLAB, right. So what we will next be doing is, we will be uncommenting this, right, and this will be using the parallel computation, right. So as we can see, it requires around 52 seconds. Remember, we have not run any optimization problem here. All that we did is, we generated 500 population member and calculated its fitness function, right. So that itself requires 52 seconds. So if we do not have parallel computation, we need around 52 seconds to determine the fitness, right. So to use parallel computation, you need to click on this icon over here, and then you will see a start parallel pool, right. So if you click on the start parallel pool, it is going to take some time, right, and now it is going to employ the specified number of cores on your machine, right. So we will be looking into that once this parallel pool starts, right. So we will look into this parallel preferences. So in the parallel preferences, things have been given. So by default, some values are there, right. So preferred number of workers in a parallel pool is 12, right. So this can be changed depending upon your requirements, you can change this. So since there are 12 number of workers, if your computer has 12 cores, it will employ all of them, right, else it will employ the maximum number of available cores. So in this case, now it has started 2 workers, right, because this machine has only 2 workers, so it has employed all the 2 workers, right. So now what we will do is, we will execute this part, right. So here what we have done is, so instead of for, we have written pair for. As soon as it encounters this keyword pair for, it is going to employ parallel computation. So here what we are doing is, again doing this exactly same thing, right. Conceptually we are not doing anything different. The second case, we are calculating it serially. In the first case, we are calculating it parallelly, right. So now the fitness function evaluation of this 500 members will be distributed on 2 workers, right. So because this computer has 2 workers, so as you can see over here, number of workers is equal to 2, so it is going to employ 2 workers to do this. So again what we are doing is, we are giving a tick over here and a talk over here, right. So it will compute the fitness function using parallel computing first. It will again compute the fitness function, because what we are doing here and what we are doing here is exactly the same, right. Only thing is that over in the first instance we are using parallel computing, in the second instance we are not using parallel computing. So now if we execute this, let us see how much time it is going to take to evaluate this, right. So in the first column will contain the fitness function, the second column will also contain the fitness function. So ideally we expect the first column to be exactly equal to the second column, because in both cases the population is same, we are only calculating the fitness function values. So computation done with pair for, it displays this because we have put this statement, right. So right now it has been able to evaluate the fitness function of all the 500 members in around 27 seconds. Whereas in the second case, since we have executed it already, we would know it will be around 50 plus seconds. So just let us wait for that to complete. Again, as your number of population size increases, the benefit of parallel computing will even be more, right, because now evaluation of 500 is divided into 2 in the first case, whereas in the second case only one of the worker in the machine is evaluating the fitness function of all the 500 members, right. So here if we see, this is 52 seconds, so it is almost half. You can also try it with a different population size. As the population size grows, the benefit of parallel computing will even be more. One of the drawback of meta heuristic techniques is that it requires the fitness function to be evaluated multiple times, right. That can be partially overcome using parallel computing. Right. So now that we know parallel computing, the question is which of the 5 algorithms can best harness the power of parallel computing? Is it same for all the 5 algorithms, or is it different for each of the different algorithm, right? So in order to better understand that, we will quickly browse through the pseudocode of all the 5 algorithms, right. So this is the pseudocode of teaching learning based optimization, right. So here we have a initial random population. We need to evaluate the fitness of all the population, right. So this step 3 can be parallelized. Over here if you see, in this case we get only one solution. First we generate one solution, we need to evaluate its fitness function, and then we need to make a call over here whether to accept that solution or not, right. Only then we will be generating the second solution, right. So the second solution is generated after taking a call on the first solution which we generated, right. At a given time we are evaluating the fitness function of only one solution over here as well as over here, right. So now it does not matter whether I have 1 worker or 100 worker, I will be able to use only one worker, right. So that way if we see, parallel computing with respect to evaluation of fitness function can only be employed over here. So here if I have p workers, I can delegate the determination of fitness function value to each of the worker, and I can quickly complete this step. Whereas over here evaluate the fitness, so here I get only one member at a time. So now even if I have 4 workers or 5 workers, it does not necessarily help me, because I have only one solution which has to be evaluated right now. Once I finish the evaluation of that, I will be able to generate another solution, right. So at any given point of time in this iteration loop, we will have only one solution whose fitness function has to be evaluated, and this is going to happen serially. So that is why we will not be able to use parallel computing over here, right. When I say we will not be able to use parallel computing, it is with respect to evaluating the fitness function value. So this is the pseudocode of PSO. Over here also we can use the parallel computation over here. Similarly, if you look into all other steps, right, over here we need to evaluate the objective function of the ith particle, right. So over here also we have only one particle, we generate one particle, we need to take a call now, right, whether that particle will help us in updating the p best or g best. Once we have taken that call, then only we will be able to generate the next solution, and we will have to evaluate the fitness function of that particular solution. So over here also we have only one solution whose fitness function is to be evaluated, and hence parallelly evaluating the objective function does not help us over here. Just like in TLBO, only one solution we have, right. We need to finish the evaluation of the fitness function of the ith particle, and then we will definitely update the population. This depends upon whether the solution which we got is good or bad, and subsequently this will change. We do not get all the solutions together, right. If we get all the solutions together, then we can employ parallel computation to determine the fitness function of each solution. In TLBO as well as in PSO, we are able to use parallel computation only in the initial case, initial fitness function evaluation. Inside the iteration loop, we will not be able to use it for evaluating the objective function, whereas in differential evolution, right. So this part helps us to create all the solutions. Once all the solutions are created, we need to bound them, and then we need to evaluate the fitness function, right. So here we have all the NP members together. Here we are not generating one member, updating the population and then generating the second member. Here all the members are generated with the old solutions itself, and when we have all the new solutions, we can evaluate the fitness function of all the new solutions together, right. So here how many members would be there is NP, right. So now I can employ parallel computation over here. Similarly in GA, right, so evaluating the fitness function comes over here when all the solutions are generated, right. So we have initial solutions, we select mating pool from that, and we do crossover, we do offspring. In none of these places the fitness function of the new solution is required, right. Once we have generated all the offsprings, we need the fitness function of them to perform the survivor operator, right. Survivor operator basically occurs at the end of each iteration, right. So now we have the new NP solutions available together, just like in differential evolution. So over here also we can employ that parallel computation, right, and again here just like all other algorithms, we will be able to employ parallel computation over here. In artificial bee colony optimization also, right. So over here we will have to perform the employed B phase and the onlooker B phase. So, if you remember the employed B phase and onlooker B phase, as soon as we generate a solution, we need to take a call. We need to evaluate its fitness function and need to take a call whether it is a good solution or a bad solution. Only if it is a good solution, it will come into the population, else it has to be discarded. So, we generate a solution, take a call and then generate a second solution. And when we are to take a call, we need to know the fitness function value. Over here also we cannot employ the use of parallel computing. So, this shows the consolidated picture, right. So, let us consider that time required for evaluating the objective function for one solution is 1 hour. Let us say we get one solution, we need to run some other simulation and the result of that simulation is expected in 1 hour, right. And now we have termination criteria that each algorithm will be allowed to perform 210 functional evaluations, right. So, this we are fixing that there are going to be 210 functional evaluation, right. And to simplify it, we have also assumed that the initial population and its fitness are available, right. The initial population is also given, its fitness is also given. So, we do not need to calculate the fitness of the initial population. So, that is given, and if we take a population size of 10, right. In this case, how these 5 algorithms benefit from parallel computation, that is what we are discussing in this slide. This part you will be knowing. For TLBO, the number of functional evaluation is NP plus 2 NPT, right. So, where NP is the population size and T is the number of iterations, right. So, this is 2 NPT. For PSO it is NPT, for DE it is NPT, this we have previously discussed. For ABC it is actually 2 NPT plus T, 2 NPT because of the employed B phase and the onlooker B phase. This T may or may not happen depending upon whether we are encountering the scout phase or not. This is the maximum number of functional evaluation in artificial bee colony optimization. To keep things simple, we are saying that let us say the scout B phase is not encountered, the limit value is so high that the scout B phase is not encountered, right. So, we are saying that let us assume that the functional evaluation is approximately equal to 2 NPT, right. Similarly, in GL the maximum number of functional evaluation in one iteration is NP, right. This may or may not happen, it can be even be less than NP, right, but we are approximating that it happens, right, because we are performing crossover as well as mutation. So, there is a very high chance that at least one of the solution would change, right, and we will have to evaluate its fitness function. So, this is the expression for each of the algorithm. If I have to perform only 210 functional evaluation and with a population size of 10, then 10 functional evaluation is lost because of the initial population. The number of iterations that I can perform in TLBO is 10, right. So, because it is 2 NPT, so 10 into this 10 number of iterations into number of population into 2, that will itself be 200, and the initial functional evaluation is 10. We can perform only 10 iterations. Similarly, all these 4 can be calculated, right. So, this is the number of iterations that we will be required to perform if the maximum number of functional evaluation is 210 and the population size is 10. So, let us say we have only one worker. So, one worker means at a time we can evaluate only one solution. So, in that case if we see, because 10 functional evaluations are already lost, we will be basically doing 200 functional evaluations over here, right. So, we will require 200 hours because one functional evaluation costs 1 hour. So, we will be doing 200 hours, right. So, same thing for DE, since the number of iterations is 20, the population size is 10, right. So, we will be doing NPT 200 functional evaluations, right. So, this is only for the iterations, the initial population is not considered, right. So, over here we will require 200 hours. So, in all the case we require 200 hours, right, because we are not using parallel computing and only one resource is available, right. So, let us consider that 2 resources are available. When we say 2 resources, at a time we can evaluate the fitness function of 2 solutions, right. So, in TLBO, in ABC, in PSO, that will not help us to reduce the time, because at any point of time we will get only one solution, right. So, now if I have 2 resources or if I have 5 resources or if I have 100 resources, it is not going to matter, right. So, for all these 3 cases the time required remains the same whether we have 1 resource or 2 resource, whereas in DE and GA at the end of every iteration we will have 10 solutions if I have 2 resources, right, then I will require 5 hours in every iteration, and I am going to perform 20 iterations, right. So, that is why this 100 hours. So, I can finish the computation in 100 hours, just the objective function evaluation, ignoring the time required for all the other operation. Let us say mutation requires some time, crossover requires some time, that is negligible when compared to this 1 hour to evaluate the fitness function of one solution, right. So, over here I will require 100 hours. In DE, if we have 10 solutions, we will generate 10 new solutions at the end of iteration 1, right. So, for those 10 new solutions, we need to evaluate the fitness function, and that can be done parallelly. Now, if we have 2 workers, right, so those 10 solutions can be distributed to the 2 workers. We can have 5 solutions for each of the worker, and since it requires 1 hour to find out the fitness function value, for 5 solutions it will require 5 hours, and again we need to perform 20 iterations. So, that is why we require 100 hours, right. So, as you can see, parallel computation does not benefit TLBO, ABC and PSO with respect to evaluating the objective function, right. So, similarly, if we extend this argument and if we have, let us say, 5 resources instead of 2 resources, now we have the capability to evaluate 5 solutions in parallel, right. So, in that case again this time will remain the same, because at any given point of time we get only one solution. So, parallel computation is not going to benefit in this case also, right. Whereas, now in DE our population size is 10, right. So, at the end of, let us say, first iteration we have generated 10 new offsprings, and now number of resources is 5, right. So, each resources can be given 2 offsprings to evaluate the fitness function, and since it consumes 1 hour, each resources will take 2 hours to determine the fitness function value, and we need to perform 20 iterations. So, for each iteration we will require 2 hours given 5 resources, right. So, for 20 iterations we will require 20 into 2, 40 hours, right. So, as we can see over here, parallel computation cannot be equally used in all the algorithms. So, parallel computing is very beneficial if we are to use DE and GA, right, whereas it is not that beneficial in TLBO, ABC and particle swarm optimization, right. So, again this is only with respect to expensive problems, wherein the time required to calculate the value of the objective function for one particular solution is very high. If you have expensive optimization problems and the ability to do parallel computation, then your choice of algorithm will also be based on whether the algorithm is able to use parallel computing or not. In those cases, TLBO, ABC, PSO need not be the best option. We can think about DEGA, or you need to modify these 3 algorithms so that it can harness the benefit of parallel computing. Now that we have looked into parallelization, let us look into vectorization, right. So, this is what we have seen so far, right. So, if we have an objective function, we give one solution having d variables, we get a scalar value, right. So, for example, if the objective function is this one, this is the Rastringent function. So, if the objective function is 10d plus sigma I equal to 1 to d xi square minus 10 cos 2 pi xi, this is inside that summation, right. Then if we code it like this, right, so wherein we get only one solution, right, we measure the length of d, we initialize f to be 0, right, and then we run this loop for I is equal to 1 to d. So, we run that summation loop I equal to 1 to d, and since it is summation, every time we calculate f and then keep adding it with f. Xi square is xd square, 10 cos 2 pi xd, this is minus 10 cos 2 pi xd, 10 to be added every time, this is 10d, and this loop runs d times. So, every time we are adding 10. So, by the time this loop gets completed, we would have added it d times, right. So, this is called as non-vectorized. So, this objective function can receive only one solution at a time, and it can give fitness function of that one particular solution. In vectorized, we can give the entire population, right, or n cross d solutions. Let us say if we are working with 2 variable problem, then we can give 2, 8, 5, 10, 6, 3, 2, 4, 3, 9. Right. So, in this case we have 5 solutions, this is decision variable 1, this is decision variable 2. So, if the objective function is such that it can return a vector, right, which has fitness function corresponding to each of this 5 solution, right, then we call this as a vectorized. So in this case the objective function is vectorized, right. So here x, right, it has rows as well as column, right. How many rows it has? It has n rows. Each row corresponds to a solution, right. So in this case if we feed this, this will be a 5 cross 2 matrix, and the 2 columns correspond to the 2 decision variables, right. So first what we do is we find out the size of x, right. So number of rows and number of columns, right. So this part of the loop is the same as this one, right, and then we have additionally this for loop which ensures that we calculate the fitness function of each of the solution, right. Since we want to store the fitness function of each of the solution, we use f of n over here. Here it was just f, here we will be using f of n, right. So this is a vectorized function. If you have reasonable knowledge of MATLAB, right, you can also understand that this will also do the same as this one, right. So here if you see there is no for loop, but we are using this dot operator over here, right. So in this case also this x can be 5 cross 2 or let us say 10 cross 2 if there are 2 decision variables. If there are 5 decision variables and 100 population member, this x can be 100 cross 5, and we will appropriately get that many number of fitness function values. So in this case 5 solutions, in this case 10 solutions. So f will be 5 cross 1 here, f will be 10 cross 1 in this case, right, whereas in this case f will be 100 cross 1, right. So in non-vectorized we can feed in only one solution at a time and we can get only one scalar value as the fitness function, whereas in a vectorized form we can feed in n solutions, right, and we can obtain the fitness function of each of them, right. So this is what is vectorization. If you consider particle swarm optimization, teaching learning based optimization, artificial bee colony optimization, we require only non-vectorized, right. Even if we have a vectorized, it is not going to be useful because every time we are only feeding one solution at a time, right. Whereas in genetic algorithm as well as differential evolution, we will first determine all the NP solutions, right, and we will have to calculate the fitness function of all of them, right. So in that case we can use a vectorized fitness function wherein we send all the members together and we get its fitness function values. So now that we have seen parallelization, so as you have realized that parallelization is beneficial especially in DE and genetic algorithm, not only in the initial functional evaluation, right, but also inside the iteration, right. At the end of every iteration we get all the solutions together and their fitness function values can be determined in parallel. So we will show you how to implement it on DE, right. You can implement the same way in genetic algorithm also, right. So DE if we see, we are using parallel computation only to determine the fitness function evaluation, right. So all the other operations like mutation, crossover, we are not using parallel computing, right. So here this is the same code which we have seen previously, right. So here we have given a tick and here we have given a talk. So tick we have introduced before evaluating the fitness function, right. So right now we will run this without parallel computation and then we will just convert this for into par for, and over here again we are evaluating the fitness function, right. After determining all the solutions we are evaluating the fitness function over here, right. So we will again be using par for over here and compare the time, right. So right now we are only executing differential evolution as we learnt previously without parallel computing with a population size of 10 and the number of iteration as 10. Right. We are using the Rastringen function. Here if we see we have put a pause of 0.1 in Rastringen function. So this will make MATLAB wait for 0.1 second before returning back this function value. This is not a computationally expensive optimization problem, but we are artificially making it as computationally expensive. So whether a problem is computationally expensive or not actually depends upon the optimization problem that you are solving, right. So over here let us just execute this. So let us see how much time it takes to complete this. Again this time will vary from machine to machine, right. So whatever time you are seeing here may not be the same time your machine would be responding it. So here it is taking around 11 seconds, right, to complete 10 iterations, right, with a population size of 10, right, and we use serial computation. We did not parallelly evaluate the fitness function value. In differential evolution, here we are initially evaluating the fitness function of the initial population, right. So, instead of this for, we have done pair for, and here if we see this is inside the iteration, again here we are evaluating the fitness function, right. So, we are sending the solutions into prob. So, let me do pair for over here. Now, we are going to execute this with parallel computation, right. Again because of the restrictions on this machine, we have only 2 workers, right. So, if we just run it, so let us see how much time it takes. So, it took 9 seconds, right. So, let us say if we increase this population to 50 members, right, and let us run with parallel computation, right. So, now 50 members means this one, all the 50 members are going to be evaluated with 2 workers, because this machine has only 2 workers, right. So, with 50 population size, let us see how much time it takes in parallel computation mode, and then we will again execute this in with serial computation, right. So, the larger the population size, the more it will be beneficial in parallel computation, right. So, it took 31 seconds, right. So, let me just get rid of this parallel computation. Let us say this is for and this is also for. So, we need to remember that it took somewhere around 31 seconds. So, now it will take more than 31 seconds. So, now as we can see, it has taken 57 seconds to solve the problem, right. Previously it took only 31 seconds, right. So, one thing that you need to keep in mind is that MATLAB requires some time to even start the parallel computation, right. So, if you are going to compare this, right, so first you need to go over here, you need to do start parallel pool. So, here if you see, this keeps blinking, it is still initializing the parallel pool. So, once it has finished initializing the parallel pool, only then if you run this code will you see the benefit of parallel computation, right. If you forget to click over here, right, even then you will be able to employ parallel computation. Because of this keyword pair for, MATLAB will start the parallel pool, right, and that requires some time, right. So, it is better that you start the parallel pool from here and then compare the time. Otherwise what is going to happen is the time required to initiate the parallel pool is also going to be considered for parallel computation, and that can be significantly high. So, that completes the discussion on parallelization and vectorization. Thank you.